He is the director of the GINAR University Center. The GINAR is this Joint Institute for Nuclear Research, which is settled in Dubna, Russia. And he will be describing this institute, this Joint Institute of Nuclear Research, as a multidisciplinary complex of large research infrastructure. So please take your seats, and he is speaking in behalf of the Division of Nuclear Sciences. But he, as you will hear from the talk, there are many branches of physics that would be very interested and motivated from the kind of analysis and experiments that take place in this complex. So please welcome Professor Kamanin.
Ok, gracias. Respetadas señoras y señores, es un honor estar aquí. Y Morelia es un lugar muy hermoso. Desafortunadamente, puedo no hablar español, por lo que, lo siento, voy a hablar inglés. Gracias. First of all, you have seen the title of my presentation, so we will speak about the not only one infrastructure, but complex infrastructures under one roof, which is joint institute, so many institutes at one place. Also, the slogan of the institute, science brings nations together. So this slogan brought us to Morelia delegation from GNR, over 11,000 kilometers, already second time this year, because of the very special reason, which I highlight at the end of my presentation. This is really nice place, and it's our pleasure to be here again. And the aim of my talk is to attract your attention to the numerous opportunities which we have in Dubna on other continent. But this continent, because of the efforts of scientific community and your government, become closer and closer. So I will speak a few words about GNI as it is. Also, since GNI is international intergovernmental organization, there is no excuse not to say about the governance model, so there will be a little bit about administrative stuff. Then I will make a spotlight review of the scientific opportunities which we have on site, and also I will mention some opportunities for Mexican researchers and students in GNR. First of all, let me say that we are located also in a very wonderful place in Russia, just 120 kilometers from Moscow, on the river Volga, which is a very ecologically friendly environment and a very nice place to live. And our campus is located on the island, which is surrounded by water from any sides. The biggest part is Volga. Welcome to GNR, welcome to our island. Please, next. Next. Okay. So this is Island of Stability. Island of Stability because we are very well-established organization since 67 years, and it is still efficiently working. But second meaning is that probably everybody knows the table of elements, and especially the bottom line of the elements, whereas the news ones. And you have seen that there is so-called island of stability. It was predicted theoretically in Dubna, and it was finally experimentally found in Dubna as well. So welcome to our island. And the last element, which probably everybody knows, is associated with a person who is alive and in full scientific power, Academician Aganesian, at the second time in the world's history when the element is given the name after the acting researcher. The first one was Glenn Seaborg, so Seaborgium element 106. And on the April 14th this year, Professor Aganesian celebrated his 90th birthday and gave a wonderful presentation about super heavy elements. Next, please. let me tell you a few words about GNR as it is seen on international landscape. First of all, there were numerous discoveries done during many years. It is idea of neutrino oscillation. It is a new particle anti-sigma minus hyperon, which was discovered some years ago. Cumulative relativistic effect, discovering new element, ultra-cold neutrons, post-radiation cell regeneration, superfluidity on nuclear matter, color changes and quark counting rule, ultra-low temperatures, and many, many other stuff I would probably not read. To some extent, it was because in the history of Institute, there were several world records in accelerations and in development of infrastructure. In particular, in the very beginning of history of our institute, there were 2 world records of acceleration. In 1949, it was 500 MeV protons, and right after creation of the institute as an international organization, we reached 10 GeV of protons. But what is most important to mention that Charter of Institute says that we are open to any partners. It is Article 1, and Article 4 says that the results of research carried out in the institute can be used solely for the peaceful purposes for the benefit of mankind. So that's what we are doing almost 70 years, and all our achievements are reflected now in the wonderful infrastructure which I would like to showcase you today. Please, next one. Speaking about GNR, its international organization in whole, in glance, we should say that international organization, intergovernmental organization, counts member states. So we have 16, also 5 associate members and 2 countries which have agreement on government level, and Mexico is one of them. The second is China. And this community, together with our partner organizations worldwide, count to 900 plus partner organizations in more than 70 countries worldwide. So we are organized in 7 laboratories with more than 5,000 people staff from more than 30 countries, and the annual budget at the moment is $220 million. So, of course, a lot of research is done locally, and I will speak about this research, but we are cooperating with many international partners. One of them is CERN, of course. So GNR contributed a lot to creation of LHC itself and to 3 big detectors, Atlas, ALICE, and CMS. And this contribution was really very remarkable. And in due history, we cooperated with CERN on 20 major projects. And in our partner network, all prominent international projects in neutrino, in particle accelerations, in neutrons, etc. Please, next one. If we look into the map of international organization, we will find GNR on the 8th place in terms of budget, but on the 2nd position in terms of the number of staff in headquarters. But if we are speaking about professional community, where we are dealing with nuclear physics, so there are only 2 international intergovernmental organizations, which is slightly different from the international project, CERN and GNR. CERN is, of course, bigger, but if you count the number of publications, we are producing annually more than 1,400. It is more or less the same number as CERN. Why? Because we have diverse infrastructure on board. Please, next one. So this infrastructure could be showcased in 7 big groups. One is Collider, which we are building now, I will say later. There also the complex of heavy ion cyclotrons, which gives the energy from 1 MeV to 100 MeV per nucleon. It is a unique reactor with mechanical modulation of reactivity. It's a deep water detector, Baikal GVD, gigaton volume detector for neutrino physics. We have a profound computer complex. We have also advanced radiobiology and life science study. Why? Because all the source of radiation are available in the institute for this research, and also for theory we have a special laboratory. I will tell you a couple of words later. Next one, please. We are reflected in the papers of international communities. We worked closely with NUPEC, with ESFRI, and let me refer to the International Unity of Pure Applied Physics report, which stated NICA, super heavy element factory, and Baikal GVD as most important infrastructures, and they are mentioned in different ways. And what is important, that this report mentioned GNR as a complementary to the global scientific agenda and addressing a majority of the goals of sustainable development. If you look to these charts, you may see, especially here, so this half, this blue one, are the research which are related to some extent to the GDO goals. And if we are speaking about international dimension, so the majority of our research are pure international or related to regions or some formations. So there are almost no national research in GNR. All our research is international. So next one, please. So when we are speaking about the complex of research infrastructures, of course, we are thinking about strategic planning. And the main goal of strategic planning is, of course, science. So we are doing science, and we have privilege to decide in our institute what we will develop. So for this, of course, we have expertise, which I will show later. But since this is complex of infrastructures and a lot of people, and also a lot of people from abroad, not only from Russia, we have to think about social environment, about conditions. Generally speaking, we are building a future campus. Well, probably we could meet in 10 years later and see how successful we are, but at least in our plans there are many things and we are realizing them. Please, next one. So strategic plan is some look to the future. It is available on website. All what I'm speaking about is available on GNR webpage, so everybody can download and read it through. But what we found that the planning of actual steps toward reaching the goals is the best in 7 years. So thus we have 7-year plan. And here are resources which are assumed to the next 7 years from 2024 to 2030. So it is almost $2 billion which are distributed as you hear. Majority of funds will be devoted to elementary particle physics and high energy physics. Of course, NICA is here. So then will be next nuclear physics and condensed matter physics. So it is a major direction of research which we have on board. Next, please. So how international intergovernmental organization is governed? It's a highest level governing body where countries are representative. We are very democratic. So each country in our committee of plenipotentiary representative of member states has one vote disregarding of the size of the contribution and size of the country. So one country, one vote. And the main function of this committee is to adopt strategy, to elect director, and to adopt the funds, which I showed you in the previous slide. Please, next. But this is a political body. When we go down to expert body, we have several layers. So in each laboratory, there are Science and Technology Council. There are a number of working groups under auspice of Directorate and also under auspice of our Committee of Plenipotentiaries. But science, we discuss in a dedicated program advisory committee following the major structure of our institute. We have a program advisory committee for particle physics, for nuclear physics, and also for condensed matter physics. And this body is pure international, so leading science from all the world represented there. Then between Committee of Plenipotentiaries, which is stick to member state structure, there is Scientific Council, which is some hybrid body. It is more than 50 prominent scientists and director of the institutions and respected academicians, etc. So all this body make the decision maker chance, which is compliant to the world tendencies. So please, next one. And here you see the distribution of our experts on the globe. So you may see here that we have also in Latin America, in Argentina, and Chile, Brazil, and in Mexico. Ana Maria Cheto is a member of our Scientific Council. And of course, we are thinking about expansion of our international organization. It's a rule for any international organization, become bigger and bigger and bigger. And now we are in a partnership with the majority of big infrastructures, but still there are a lot of interest from all around the world. And we will manage, next week, please. We will manage this in this way. So it's a region approach, which states that to further developments, we will take into account the interest of our existing partners, of our member states. So that's outreach for a larger community worldwide. Well, but now probably it's time to finish with this official representation and switch to the scientific agenda. So what is interesting to member states and to our future partners? Please, next one. Let me speak about all our 7 laboratories, one by one, spotting the most interesting facts about them. Let me start first with theory, because when we are speaking about infrastructure, theory always comes to the last place. But in our case, let me put it first, for the following reason. So theoreticians are really energetic and mobile community, and our laboratory is more than 200 researchers, what make this laboratory the biggest theoretical institute in the world. And the qualification level of this laboratory is very high. So we have 80 PhDs and 90 second PhDs, so it's a doctoral level, what we say in Russia, full doctors. And scientific activity of the laboratory is very high. So they produce up to 1/3 of the publications which we are producing in GNA, making a lot of conference and pushing our experimentalists to work further. Next slide, please. And the structure of theoretical laboratory complying with experimental facilities which we have on board. So we have theory of fundamental interactions, theory of atomic nuclei, theory of condensed matter, certain mathematical physics, and they are relevant to the facilities in our laboratories and activities in our laboratories. So it's supporting NICA, it's supporting neutrino physics. There are some application for lattice QCD calculations. And also for young researchers, we have Dubna International Advanced School for Theoretical Physics. Please, next slide. Now let me come to the Collider, NICA. I will not speak much about particular results of Collider. I will only say that this Collider is, to some extent, from the technical point of view, similar to other colliders like LHC with this experiment All-Star in BNL. Of course, it's dedicated to certain scientific topic, which I will say later, but the most important message about the collider is that it's already operating, at least some part of it. One collaboration with fixed target is already taking data since 2018. One of the 2 biggest detectors which will get in our collider, multi-purpose detector, where Mexico is one of the participating body, is ready to be commissioned. And the second big detector, spin physics detector, is in plan, so it will be ready in 2028. So at the moment we have unique opportunity. If you are interested to join the team of Collider, you have choice. Either to join to the body which is already taking data, or which is commissioning and doing a lot of hand-on work, simulations, or to join the future plans. So it's a good choice. Please, next. Let me also mention that the cost of Collider is $500 million, and it's a basic configuration. So together with detector and contribution from the collaborations, it will be something like a little bit less than $1 billion. So most important, what this collider will do in physics. The first detector, which is baryon matter detector, so-called multi-purpose detector, it deals with hot and dense baryonic matter. So if you look to the diagram, phase diagram, where you have net baryonic density and temperature, the transition between hadrons and quark-gluon plasma is very interesting region. And you may see here that prominent institutions like SPS and so on, Rick Bess in Brookhaven, 600, it's a FAIR, which is also our brother project, so we are working in Collider more than they building fixed target detectors. They are looking to this region. But probably NICA has advantage that it was dedicated to this research, and its sensitivity spreads from low temperatures up to the critical point. So if we will be lucky, we could really do a lot on this track. And the energy on center of mass system for gold isotopes with plus 79 state should be 11 GeV per nucleon with very good luminosity, 10 to 27. In principle, we will accelerate the variety of other ions, but this is a benchmark. SPD is a spin physics detector, which is also working on the field which is populated. And our next partner is also RIC in BNL. And they're already operating, but the lowest energy is 63 GeV per nucleon in center mass. So our energy will be 27 and less. But advantage of NICA will be that we will not only have polarized protons, but also deuterons, and there could be collisions, deuterons, proton deuterons. So the variety is much bigger. And also it should be relatively soon. So it is very competitive. So please, next slide. And let me mention something what is important for our international organizations, that our detectors, which are consisting of more or less the same structure as you typically heard from other detectors. So it's a colorimeter, tracking, time of flight system, scintillators array, etc. So that's why I will not go much in details. I will only tell that the collaborations are already established and grown. BMN is already working. MPD is more than 500 participants. MPD meeting was just a few days ago in Serbia, where a delegation from Mexico also was. And SPD collaboration is already established and making configuration of the detector. So this collaboration is usually drivers of further development. So please, next slide. But let me tell you that if you have seen of the first slides that there is a benchmark where our systems were switched. So now we are already on the fourth technical run of the booster with nucleotron. So we have injector, booster, nucleotron, and then transition to collider. So collider itself is not yet commissioned. It will be only next year. But we are already working with booster and nucleotron with HELAC. And we are already producing data. And this year, we already submit the first publication from BMN collaboration, which was dedicated to production of pions and p-mesons and k-mesons. And you may see here that there is good particle identification, good signal for lambda hyperon, K0, etc. So most important at the moment that we are already practicing and taking data, and we are ready for commissioning of the MPD bigger detector. So please, next one. So the second important, what I would like to mention with you is that further improvement of the beam is electrical cooling. So just recently in our technical run, we commissioned the electronic cooling of our heavy ion collider. And you may see here how the diagram of the beam look without cooling and how with cooling. So of course this increase the luminosity and efficiency of the collider. So the basic of our collider is a fast oscillating superconductive magnet, which is know-how of GNR. So but as usually, such a project could not be done domestically, so we are working with big international team, contributing also our know-how. Please, next slide. What is also to mention that beside of fundamental physics, beside of particle physics, hot baryonic matter, spin physics, we are very much focused on opportunities for applied research. And we already made several stations where we could get different beam energy and different ions. One is 3 MeV per nucleon, which is already available on HELAC. And this is for life science, for testing of decapsulated microchips. The next station is intermediate energy, which is on nucleotron on the next cascade. The number of ions is already available. And we could work with not decapsulated microchip, which is very important for space industry, for testing of radiation hardness. And there will be also high energy setup with 4.5 GeV per nucleon for a variety of different experiments. So this is called Ariadna Applied Research Infrastructure for Advanced Development at NICA facility. So this acronym stands for Ariadna. So please, the next slide. And important message that, again, it's not a plan, it's already working. So recently we got a first beam, which is shown here on the radiochromic film with dimensions of 3.5 by 3 centimeters. And the collaboration, Ariadna, is already established, so everybody can join. The main task will be radiation material science, composite material, radiation modifications in high temperature superconductors, et cetera, so it already is a business of collaboration to find proper applications. The first beam which we got was Xenon 54 plus at 3.8 GeV per nucleon. It was at the beginning of this year. So please, next. Let me finish about collider with this set of pictures. So you could imagine, what is collider? Collider is a big stuff. So the experimental holes, there's a magnet, so here's a booster, here's a hole of MPD magnet. So it's huge stuff. But there is some result which I wanted to mention, which is very small, but makes the performance of our future collider is much better. Next slide, please. As usually, development of an experimental technique is rich of different spin-offs. And this is one of spin-off. Our engineers and researchers develop a compact precision laser inclinometer. What is that? So you know that Earth's crust is breathing. In particular, there is a lunar tide and solar tide, and there are also some vibrations, oscillations of surface, and this become visible, for example, in CERN and LHC. How to tune the collider to account for the breathing of the Earth, to inclination. For this, you should measure very tiny inclinations, which are better than solar tide. And this is exactly developments which is shown here. So we already used this inclinometer at CERN transport tunnel. It was used in Virgo experiment for searching of gravitational wave. But what is interesting that, of course, applications of such devices typically wider than it was thought initially, because now there is a collaboration which is thinking how to use its network of inclinometer for predict earthquakes. Very interesting. We will see. Please, next slide. The other spectacular infrastructure is located not in Dubna. It's on Baikal Lake. So when you will come in March or April to Baikal Lake, you will see something like that. Of course, you do not see detector because detector is underwater. But what we are doing, we are searching for extragalactic neutrinos with energy of several tens of tera electron volts. The source of these neutrinos is still unclear, but understanding of the source will elucidate understanding of formation of galaxies and bring a lot of breakthrough discoveries in cosmology, in basic understanding of the world. So here is how we are doing. So you see here our optical module deployed. Please, next slide. And this is how detector is organized. Why Baikal? Baikal is the deepest sweet water lake on the Earth. So the depth of Baikal is at certain places more than 1.5 kilometers. So we put anchors on the bottom of Baikal, put strings at the level more than deeper than 700 meters. It's absolutely dark there, so there is no background from light and also from radiation from the surface. And at the moment, we have already 3,500 optical models deployed, arranged in 12 clusters. So the size of the model you can judge here. And unfortunately, it's possible only to work 2 months on the ice. Why on the ice? Because the positioning is very precise and it's easy to use heavy machinery for maintenance and deployment of strings with optical modules. But what is the main advantage of water? You understand that we are comparing our detector with ice cube, which is complementary infrastructure on the other side of the globe, because angular resolution in water, in clear water, which is also temperature stable, is much better. So we have resolution for muon tracks half degrees. In ice cube is more or less up to 1 degree. And also angular resolution of shower directions is impressive. So we have to 3 grads, and ice cube, it is more than 10. So, but we are working together as a multi-messenger observatory, and in particular recently we confirmed the observation of ice cube diffuse neutrino flux with a 3 sigma significance. Well, again, it is very spectacular physics because it's 5,000 kilometers away from the center of the country in a very nice place. And our team, when we are coming to work, look like a fisherman team. But they are doing very interesting research, and we reached already 0.6 cubic kilometer. So our goal is to reach 1 cubic kilometer and then to think about the GVD prime or GVD2 project. Please, next slide. But it's not the only infrastructure which is located outside of GNR, which is dealing with neutrons. Again, we are participating in many international projects like Edelweiss and others, but I'm speaking about our domestic project, where our role is most important. And on the atomic power plant, which is just 300 kilometers to the northwest from our institute, we have privilege to work under the core of industrial thermal power reactor. So the way how we did it was because we applied for this in the construction phase. So after a reactor is completed, so no one can bring anything inside. So you see here one of our detectors, which is called DANCE. It's a detector for study of neutrino oscillation. It could be moved up and down under the core of reactor. And second opportunity for this detector is to monitor the state of fuel, because we can make a decomposition and find how much plutonium is there. It is other spin-off application of this detector. You may see the size from this picture. So there are quite a number of other applications at this power plant, but let me go further to the next slide. Laboratory of Neutron Physics. So there will be a talk by Professor Kucherka tomorrow, so that's why I will not speak much about this laboratory. I will only tell that this unique reactor with mechanical modulation of reactivity, average power of this reactor is 2 megawatt, but in pulse, which is 5 times a second, is 2 gigawatt. So next slide, please. This make the flux of neutron on the surface of moderator 10 to 16 per second per square centimeter. And of course, it's used in a number of applications for nanosystems and soft matter, atomic and magnetic structure, lattice and molecular dynamics. And there are also some applications for nuclear physics, which I show later. This laboratory dealing not only with neutrons, but of course it's a major facility. We have also some gammas, we have X-rays, we have diffractometer, and we have also Raman spectrometry. What is, back to reactor, what is important, that reactor has user program. So everybody can apply. And if your application is successful, you would give a beam time. Please, next. What we are doing at this reactor. So first of all, follow the people who founded this laboratory, which is Ilya Frank, Nobel Prize laureate. However, he got his Nobel Prize for Cherenkov light, not for neutrons. Dmitry Blahintsev, the first director of our institute, who invented this principle of mechanical modulation. And also Fedor Shapira, who is founder of ultra-cold neutrons. We were always thinking about ultra-cold neutrons, and with further modernization of our reactor, probably it will be possible, but we are working now mostly with cold neutrons. Neutron scattering for condensed matter studies, there will be exactly the talk, so that's why I will not touch it. I will only say that there are also a number of nuclear physics applications. Probably such a pulsed reactor is not the best for nuclear physics, but still we are doing a nice job on nuclear data for energy and astrophysics, fundamental symmetries violation, in particular this in multi-body fission, and there are a number of applied research. And we are thinking about new reactor. Why? Because very soon, in 2030, in Europe, for example, there will be only 3 acting reactors and probably 2 new ones. One will be in Russia, and one will be in Lund, ESS. So there are plans on this end of the world. So Oak Ridge should make the new reactor in 2037. So, but it means that the number of accessible neutron beams will be very much limited. So that's why we are thinking of using our technology, this know-how on the mechanical modulation of reactivity with a Neptunium fuel, and we are making now a feasibility study, and the goal is to have the best pulsed neutron source in the world by 2037 with a brightness 10 to the 15 for thermal neutrons. So, of course, it's ambition plan. Let's wait until 2037, and we'll see if it will come through. Please, next slide. Just a couple of applications. So one of applications which is very famous in our institute because the professor who chaired is leading professor in the United Nations programs for clean air, Professor Fantasieva. This facility is called Regatta. This is pneumatic transport of samples to reactor and back with a measurement of Newton activations. The majority of work was done with mosses because mosses have no roots and they absorb pollution from the air. And in particular, this way we make maps of pollutions, for example, in Europe. And you can compare this in the 90s and recently. So the statement that air become cleaner everywhere. And we are investigating what are the sources of pollutions right now. But there are many other applications of this method in archaeology, in forensic science, etc. Please, next one. This is also something quite different. So we are speaking about infrastructure when it's something on the ground, but our facilities are flying in the space. And in particular, we took part in the Martian Odyssey with a compact generator of neutrons. It's a compact accelerator of deuterons, which produce up to 10 to 11 newtons per second. And thus you can irradiate soil. And if there is a lot of water inside, the albedo of neutron will be strong, and you will see a lot of scattered neutrons. So these neutron generators, together with measurement of scattered neutrons and gammas, is a compact detector. So that's why it was located on the Mars orbiter and in the Opportunity rover, which seeked water in the Gale crater. And here you see the stand, how we calibrate the data from the Opportunity. So please, next slide. There are many of others. This project in the extraterrestrial science was done together with Laboratory of Radiation Biology, which is the youngest laboratory in our institute. The need for such laboratory came from the manned space missions to understand how the space radiation acts on the central nervous system. And the privilege of our institute is to work with mammals and primates. So we have mice, we have monkeys, and we have all possible sources of radiation available. So thus, this laboratory became a laboratory level in the GNA, which is the institute level, and it deals with molecular radiobiology, radiation genetic, radiation cytogenetics, and many other stuff, including also therapy. So we were pioneers in the proton therapy of deeply lying brain, and we are building now the superconducting facility to continue this research. Please, next slide. So, information technologies. Our information technology complex is also something unique because we have combinations of all possible computer infrastructure at one place, which are working together. And recently, we got our own supercomputer, which is 100% liquid cooled. And this is highly ranked in the listing of I/O, so input-output supercomputer I/O 500. So it is quite on the top. And after modernization, it's again on the top. This is a very new one. It's just 5 years, and it was modernized last year. So please, next slide. So this is a supercomputer, which is called Gavarun, after famous researchers. We have cloud infrastructure. For many years, we have worked on the tier 2 level. and we become the best tier 2 in Russian Federation and also very competitive on the world side. But recently it was clear that we are able to provide tier 1 surface. It is one of the 13 tier 1 nodes for CERN worldwide, and it is located in our institute. So how to work with all this together, because it's a heterogeneous infrastructure. So we are using direct interware and which connect all the resources, and also not only computer engineering, but let's say ground engineering is very strong, because all this should be available each moment, 7 days a week, and all the year round. For that we have very strong cooling, power supply, uninterrupted power supply, and many other stuff. Please, next slide. So you see here how our tier 1 node for it is working for CMS is ranked among other CMS tier 1 node, and it's a very good performance. So if we are speaking about tier 2, I said already that it's the biggest in Russia. You may see here there's a blue one. And if we are speaking about share between the share of the jobs between the different computer nodes, so you may see here how we are loading our clusters. So tier 1, tier 2, supercomputer and cloud infrastructure. So let's come to the next slide. Please skip it. Next one. Of course, since it is so big and it is so diverse, what we are doing with that? So there are numerous applications. Probably one presentation would be not enough to say about all of them, but let me say about one. Supercomputer is used for simulation of quantum computers. So we are using some algorithms for simulation, and the capacity of Gavarun is sufficient CPU for 38 qubits and GPU for 34 qubits. For most of applications nowadays, 40 qubits should be sufficient. So our share in this job is not to create quantum computing, but to create algorithms. And one of the interesting applications of this algorithm is tuning the collider. So could you imagine how many degrees of freedom in the magnetic elements in the collider are? Thousands. So it would be, in manual mode, almost impossible to keep this running smoothly. So we did it with the aim of quantum computing. So please, next slide. And now I came to the last laboratory. So since we are approaching nuclear physics session, this will be a little bit more about nuclear physics laboratory of nuclear reactions. So here you see the diverse applications which we are doing in the lab. But let me focus your attention to the available infrastructure. So we have two big cyclotrons with 4-meter pole, U400 and U400M. This produce average energy of heavy ions of the tens of MeV per nucleon. This one up to 100 MeV per nucleon. There is implanter located here. I will tell later, 1 MeV per nucleon. And the new facility is factory of super heavy elements, which is tuned specially for production of beams and facility for super heavy elements. But there are also something else, microtrons, which is electrons, 25 MeV, and many small equipment and stuff like that. Please, next. Here's a nice view of our super heavy element factory. What is the main key issue of the factory? That for production of super heavy elements, in a way how all the world is going now, one needs very intensive beams of calcium-48, titanium-50, and other neutron-rich elements. So we could reach up to 6, 10 to 13 calcium-48 beams, particle microamps, which is it is not particle mass, it's a particle per second, of course, which is a world record. So please, next one. And since this new facility, we built also the new separators, new detectors. This one separator is gas filled. So why gas filled? As you understand, when you have a bunch of different ions, it's better than they are thermalized and then it's separated, they will come the same place. So it's trivial stuff, but it's realized in the gas field separators. And our immediate plans to complete the experiments with already available and known isotopes, but we could already study the properties. And we are preparing synthesis of element 119 and 120. Why it's interesting? Because it is close probably to the absolute end of this super heavy element story. So we will see. Next slide. And this slide is illustrating how one can make chemistry of a single atom. So as you know, super heavy elements are born and detected one by one, let's say one per month or one per week, if in a good case. So how to think about chemistry? For this, we use the technology of the thermogradient detector, when on one end we have cryogenic temperature and on the other end is normal temperature, and we compare this with known stable elements. Please, next one. Since this way of production of super heavy elements is very difficult, and the cross-section are very small, there is another promising direction, which is fragmentation in the multinucleon transfer and fragmentation in the reaction with very massive ions. For example, uranium plus uranium. It will cover not only the area of interest where super heavy elements are, but also blank spots on the nucleate map. But in order to make preparation, of course, we should make a lot of tests, and one test is underway. So we are preparing experiment uranium plus uranium at 1.6 MeV, 1.6 GeV in the laboratory system, and it will look so that uranium hit uranium target, and then we are registering at certain angle the tin lead nucleus, and we see fission of nobelium. So this should happen at the end of the year. Everything is prepared. So please, next slide. A lot of underlying theory is done in the laboratory of nuclear reactions. And this theory, because we have our own theory group, resulted in a web interface which is available for everybody, which is called NRV, Nuclear Reaction Video. And if you go to this site, you will see how amazing is this system. So you can study nuclear decays, nuclear reactions. You can see properties and the nuclear map. So this is a very useful tool, especially for education purposes, but also for planning of experiments. Please, next slide. So all about super heavy elements is here. But another very important point of our efforts is here, super heavy light elements. Please, next slide. It's done with separators, and in our case, a separator which is called Akulina, accurate beam line, separating line. So we have two. One generation is already old one, but we built a few years ago with the help of Sigma Phi Enterprise this double achromatic beam line, and also the measurement station outside of experimental halls, which provides low background. And we increase the performance of the channel. Please, next slide. And one of the most interesting objects is hydrogen-7. Why hydrogen-7? Because it's the heaviest available resonance of hydrogen. And decay of this resonance could give you some insight about multi-neutron decays. In particular, it could be emission of 4 neutrons. And it has some connection to the story of tetraneutron, which is already discovered, but it's still far away from the complete story. So it could be 4 neutrons at the same time, so it corresponds to the line which we measured here. It could be 2 neutrons plus neutrons. It could be other combinations, so we could judge this from the spectroscopy. For that, we have already 2 experimental campaigns with 2 telescopes and codoscope here. And the next campaign was with a better performance. So what we're doing, we are measuring in coincidence helium-3 and hydrogen-3. The missing is neutrons, and the impinging particle is helium-8 from the beamline on the target, which is also exotic. So we have cryogenic target with hydrogen, deuteron, triton, and helium-3 and helium-4. And Triton is absolutely unique. There's only laboratory who has this tritium beam is GNR. So you see here the facility. So we have time of flight. We have here the target. We have this telescopes and also steel beam-based neutron detectors. So please, next slide. So on this chart, you see all the nucleons which were studied in our reactions. And here is a plan of research. So there's quite a number of interesting things like neutron halos, beta delayed decays, and stuff like that. A lot about cluster state. But what to do, how to be compatible, how to be competitive when we have such partners like RIKEN and big RIPS. So please show the next slide. A lot of interesting technologies are used. For example, we amended our beamline with a radio frequency kicker, which make our beam much cleaner after separator. Also, we put zero angle magnet to clean our reaction products and many additional interesting technical details, and also cryogenic target, as I told you. So we are expecting the next generation of the target, and the full performance of this facility will be in 2025, so very soon. Please, next slide. Besides fundamental research like that, we have also a lot of applied stuff. I will not show you much because my time is over. I will only tell that at this special facility, we are making holes in track membranes, so in membranes, and this know-how of so-called etched track membranes, which is either interesting source for foil for filtration or for quasi-regular nanostructures. And to study this, we have special nanolaboratory. And concerning microtron, let me mention that it's not only applied research, which is typically done with electron accelerator, but there are also some fundamental research. For example, we are studying photofission and in particular long-living shape isomers in fission fragments. Please, next slide. All our cyclotrons we built ourselves. And not only for ourselves, but also for our partners. This shows the very interesting, very nice cyclotron center, which we built in Kazakhstan and Astana for our member state, and it became flagship project in Kazakhstan. Please, next one. And together with this facility, we educated a team of approximately 30 researchers and engineers, which become a core of this institute. And I came to the last point of my presentation about education programs. So we have University Center, and its mission is dealing with students which should get access to facilities, dealing with development of partnership using education projects. We are dealing with science popularization and with improvement on skill. In particular, we have engineering practicum for those who are interested to study how to make hand-on work with detectors, with accelerators. Please, next slide. Here's the opportunity for students. We have the main mode is so-called sandwich program. So when university send a student and we provide a course supervisor, and the thesis is done back in the university. But we have dedicated program in GNR. One is international student practice, which is 3 weeks in GNR. This is selection and payment is done by sending party. Interest is an internet-based program, so quite a number of young colleagues from Mexico already participated. And START is in-person program when we are selecting applicants and they are coming for 2-3 months to make their practical research in GNR. So this is variety for students. Of course, students can join any running project, and this is a point of special attention. Let's go further. Next slide. Our young researchers make 2 conferences a year, especially dedicated to young researchers. Please, next one. And we understand that it's not possible to bring all those who are interested what GNR is doing locally to GNR. So spreading of information and selection of participant needs to organize local expertise. So thus we came to the idea of information centers of GNA. At the moment we have already 10, 4 of them are outside of the hosting country of GNA, outside of Russian Federation, and next year we should get another 5 new information centers. So it is growing and it's already an object of special care. Please, next slide. And that's why we organized also the program for decision makers, for ministers, rectors, deans, and contact points. So this program already successfully ran 23 times. You may see here how many people already participated, and the level of these people, it already covers a significant part of the map. There is still nobody from Mexico, but we hope very much that if here any decision makers, so please come to me and we will agree about the opportunity to come. And in 5 days, we are showing all the institute, all the major facility, reading, lecturing, making a meeting with our leading experts, and showing how life in GNI is organized. And please, next slide. And the participant will see that it's not only science on the good level, but also international culture. Next slide. Sport and social activities on a very good level. And that's why we already decided with CONACYT, please, next slide, to focus attention on the opportunities for Mexican researchers and students in GNA. And at this year, at February 16, at the Marginal Scientific Council, there was agreement signed, and under this agreement we established coordination committee, which is dealing with selection of projects, and the first official meeting of this committee dedicated already to result of this selection will be just next week. So we hope very much that all these endeavors, which were done by Directorate of GNA, by our laboratories, and also our colleagues here in Mexico, will lead to the numerous opportunities for you to use our infrastructure, to be acquainted with GNA, with Russia, and we welcome you to come. Please, next. It is almost the last slide. So the situation looks the following. So GNI is like a ship, and CONACYT already purchased several tickets, so you just have to fetch them. So here is a number of sources for information about GNI. The major one is a topical plan of research. So you can download this from the web page of GNI and see in details what we are doing, how we are doing, and who is doing that. And for those who are brave enough, please, the last slide, please come to GNA anytime. So winter in Russia is also very beautiful. And here's a view from our administration building around the new year. So welcome to GNA, welcome to Dubna. Thank you very much.
If anyone has some questions, please approach to the microphone.
Well, thank you, Dmitry, for your fantastic presentation of the Institute. You tried to feed an elephant in a cup of tea. You did a very wonderful job. Probably there's people who would like to make a question in Spanish. If there's anyone, then we can try to translate for you. I have a ton of questions about cyclotrons, nuclear physics, charge states, but then I guess I'll leave my questions for later when I...
It will be my pleasure to send you all the data.
Okay, thank you very much. But really, grab the opportunity to talk to Professor Kamanin, and if you have any questions, come forward and ask.
También si quieren preguntar en español, podemos ayudarles a traducir si alguien no se atreve a preguntar en inglés.
Hi, well, first of all, thank you for that presentation. Well, my question is directed towards the Center of Computing that you mentioned. Are there plans to give resources to students or researchers to use it? Like, for example, specifically to simulate those quantum disk qubits, for example?
Yes,
Well,
yes, definitely. There is a plan to give access to anybody who is interested. The only intermediate step which is needed is to make a joint project. It's already a function of our senior gentlemen participating in the coordination committee in CONACYT. So as soon as we have project established, all the resources will be available for the purposes of this project.
so is it gonna be? Well, I'm thinking about like this project that Alura and some other and companies have adopted, that they can lend some servers, some part of the servers.
Okay, so since our computers are very much used for the big projects, yeah, so we could not provide computer time for individuals. But as soon as there will be collaboration established between Mexican institution and GNA, we will find a way to allocate necessary capacity.
Thank you.
Hello, thank you very much for your presentation, and I think it's very interesting and exciting the fact that exists some organization as what you just presented to us, and I'm a student, and I'm very excited about the research in neutrino detection, and I imagine that you are detecting it by using Cherenkov light?
Yes, sure.
And I would like very much you to explain a little bit more to us and about this project and how we can join the steps we need to follow, or the people we need to contact to be more
Okay, so thank you for the question. In fact, since our charter says that we are open to all interested organizations, so if your university or if your research organization is interested to collaborate with us, we are ready to discuss it, institutional collaboration. As soon as such collaboration is established, there will be plenty of opportunity to get trained in GNA, to come to experiment, to participate in distributing and processing of the data. But as individual, you still have the opportunity, especially for that I shown this start and interest, and also student practice. But student practice is something what need to be organized by CONACYT or somebody else. But start and interest are the program which already used. So here we have young gentlemen who already either participate or applied. So you can apply, you can choose topic which you are interested, and if you are lucky, if you will be selected according to your portfolio, you will be invited to participate in our research. So the opportunity is right here.
Okay, thank you very much.
Thanks for the talk. I have a question, a particular question. You presented some detection of neutrinos and looks like a crystal. They have a particular geometry, and my question is, there is a relationship between the geometry of your detection with the kind of neutrino you detected? It's like this.
Okay, but what is on your picture? This is geometry of Baikal GVD. So Baikal is a huge amount of water, and it uses clear water as a detection media. But your question was about the compact detector and geometry. This is dense. It's a small cubic. I don't think that efficiency depends very much. But since the flux of neutrino is 10 to 20, something like that, at the core of reactor, so we can still use a small detector to see something, because the flux is really huge.
Yeah, my question is because I see some new kind of crystals in the hyperbolic space, and looks like likes detections. So I guess there is a relation between this and this, but it's something different. This is for the behavior of the neutrino in the water. Yeah.
Okay, so this is not crystal, this is plastic.
Yeah, it's plus. Yeah, I see the pattern and I guess this is like a crystal, but it's not.
Well, I will forward your question to colleagues who are dealing with that, if they're interested and they are aware.
Thanks a lot.
Did you apply for START for neutrino physics? Please give me your contact.
Hi. Well, I just want to ask if there's any kind of opportunity for a kind of internship for someone when he finished his bachelor's degree.
This program, International Student Practice, is for bachelor and the beginning of master. START is for master and beginning of PhD. But I think that if you're interested in serious involvement in this physics, the best way is to find a supervisor here who is communicating with GNR. So here there's a lot of senior colleagues who can help, for example, Professor Alfredo Raya, or Professor Alexandra Ayala, or Milena, and many others. So there are already expertise about GNR among researchers in Mexico. So that will be the most profound way. If your supervisor is connected with us, there will be opportunity for you to participate in joint research and probably to come to GNR.
Okay. Thank you so much.
Hi, and thank you very much for your talk. Regarding the last question that you were asked, I would like to know if there's a way to know which researchers are currently in talks or in contact with DNR. Is there a way to look it up on the internet or on the DNR website?
In GNR website, definitely. If you look to the topical plan, you will already find several names which are from Mexico participating. But probably you can address your question to Professor Raya immediately.
Thank you very much.
Maybe it's indirect way to reach our projects. But you see that we are not making open program for students just to come to GNR. So we are working with these institutional partners.
All right. Thank you very much.
But it gives you more opportunities. Just to amend answering to this question, let me tell you that, of course, we have our own fellowship program and our postdoctoral program, but probably it's a little bit for later stages.
Hi. Thank you for the information. It's very interesting, and especially for me because I want to study something about the nuclear physics. And well, it's specific. I want to ask you how many areas the application of modelage computing, because well, it's something I have interest in. Well, yeah, and how can I application the modelage computing?
Okay, so the question is basically the same as it was previous one. So may I give additional advice? So after this meeting, which will be next week, I think we will have some results which already very certain which projects are supported, and if your interest will be among of supporting project, you can start immediately. Otherwise, you should initiate your supervisor to contact us.
Okay.
It works. It works in other countries, so it will be working in Mexico as well. Sure.
Okay, thank you.
Hi, nice to meet you. Excellent presentation. And I don't understand why the plastic BC have a hexagonal form.
Okay. Very, very clear, because you have to occupy all the space without holes. That's why it should be either square or hexagonal.
Hi, thank you for your time. I have a question. Doing GNR are working in some nuclear energy projects?
Yes, we are not directly involved in energy generation, but we have several projects related to technologies. One of them is subcritical assembly. So we are studying multiplication of particles in uranium block. One of projects is about radiation hardness, because you know that all the composite materials like ceramics, etc., they should be stable and should be long-living in the reactor. And testing of radiation hardness is the best with heavy ions, because heavy ions accelerate the process 1,000 times. So there are probably some other research, computation and reactor technologies. So, but not directly energy generation.
Okay, but the investigation of all the GNR can get involved into that very easily?
Well, investigations is used because we are contributing also to the nuclear data.
Thank you very much.
Any further questions? But still, the gentleman microphone.
Hi, thank you for your talk. Are there any opportunities for a bachelor's or master thesis?
Yeah, definitely. It's a main mode how we are working with students. But again, so as soon as we have cooperation, for example, we have cooperation with UNAM, and with number of other universities. So among the topics where they are already involved, you can come immediately. So you just have to contact supervisor and agree with us. To other topics, we still have to push a little bit your professors to establish link. But Professor Raya could probably forward you to the next person who has connection with GNR. Sorry for answering such questions that we could not directly pick you. For this, we have start and interest program. For the rest, we have such institutional connections. Because we are not university, we are a research organization, and our main purpose is to provide high-quality research. So that's why the model is very simple. So we have institutional contact with the university. So university contributes something to the collaboration together with the manpower is with students. So this could not be one without another. I don't think that it's something new for you. Thank you very much.